let me also address the issue of oversampling the signal. Okay, so that means going at a sampling rate that is higher than what you need to. Okay, so oversampling the signal. Oversampling. Okay, oversampling, what I mean is omega s is greater than Nyquist rate. Nyquist rate. Now notice that when omega s equal to Nyquist rate, then the reconstruction filter was a ideal filter. The reconstruction filter looked like this, minus omega s by 2 to omega s by 2. Okay? This is an ideal filter. Ideal filter. And such a filter is not realizable in practice. So, what do we mean by this? We cannot get filters which have got a transition from pass band to stop band, which is exactly like a straight line. What we are likely to get is a filter which has got a response that looks more like this. There will be some factor. So, this is a ideal filter. This is an ideal filter and this is a practical filter. The flat portion is okay, but this is a realizable filter. Realizable or a practical filter. Practical filter. Okay. So, now the important aspect of why should we sample at higher than Nyquist rate. So, if you sample exactly at Nyquist rate, what you will get is the copy m equal to 0 and m equal to 1. So, this is at Nyquist rate. At Nyquist rate. Okay. This is corresponding to m equal to 0, this is corresponding to m equal to 1, and there will be a copy which is m equal to minus 1, this is m equal to minus 1. Okay. So, the only filter that can remove all the copies without distorting the original signal is an ideal filter. Okay. In this case, only ideal filter will satisfy. So, if you are at Nyquist rate, you need ideal filter, ideal reconstruction filter. Ideal reconstruction filter. Okay. Now, if you have over-satisfied Nyquist criterion, so if you are at greater than Nyquist rate, then what you will see is you will have a situation where the copies of your signal are like before, but there is a gap between the copies of the signal. So, this is omega s, this is omega n minus omega n, and this is omega s by 2. Okay. You can see clearly that omega s by 2 is greater than omega n. This means omega s, the sampling rate, is greater than 2 times omega n. So, which means that omega s is greater than Nyquist rate. Okay. So, I hope you are able to see, the more you over satisfy the Nyquist rate, these spectral copies are going to move further and further away from each other. Now, if I want to apply a filter, then I will have a filter that goes flat from minus pi by n to pi by n, and then will drop off to get a practical filter. Okay. So, this is a ideal filter, this is a practical filter. So, I hope you are able to see that the presence of a gap between the copies of the spectrum is extremely important for us to be able to build practical filters. Okay. Now, you may think that maybe this is all theory, where do we really see it in practice? Actually, if you do listen to music on a CD player, so a compact disc or a CD player, you will actually, this principle is utilized there. So let us see how this principle is utilized. Okay. In compact disc, the assumption that the audio signal that we want to preserve is in the range 0 to 20 kilohertz. 0 to 20 kilohertz. This is the range of the signal that you want to preserve in an audio signal. So according to this, if you were to use a discrete time signal, discrete time audio signal, the Nyquist rate will be 40 kilohertz. 40 kilohertz. Okay, but of course you cannot play back discrete time samples. You have to convert it into a continuous time signal before you can play back. That's what you can play to a speaker. So there is in a CD player, when you have playback, you have to convert from discrete time to continuous time. So basically this is the process of reconstruction. Reconstruction process is going to be present. Okay. So what is the sampling rate that is used in a compact disc? It has to be at least 40 kilohertz, that only then that's Nyquist rate. So the sampling rate of a CD player, sampling rate is 44.1 kilohertz. Okay. So what does the spectrum look like when you look at it in the sample domain? It has from up to 20 kilohertz, so minus 20 to 20. The first copy of the signal will be at 44.1, and these are all in kilohertz. So if you now look at the first copy is centered around 44.1. So this frequency will be 24.1. So there is approximately 4.1 kilohertz between the signal that you want to keep. So this is the m equal to 0 copy of the spectrum, this is m equal to 1. So what we will do is we will use a flat response, and after that you make sure that the filter goes down so that it will remove the unwanted components in a very simple and effective manner. In fact, CD player does something even better. CD players actually instead of 44.1, they use in the reconstruction process, the first step that they do is to convert from 44.1 kilohertz, they increase the sampling rate to 4 times, 176.4 kilohertz. Okay. So now what you have is a discrete time signal which is sampled at 176.4 kilohertz, very high sampling rate. So where will be the copies of my signal? My m equal to 0 as always is sitting here. The m equal to 1 now is sitting quite far away. Okay, it is centered at 176.4 kilohertz. Okay, this is at 0. So notice that if you have so much separation, you can actually make sure that your the unwanted copies can be very, very effectively removed. Okay. Now that is not the only reason they go to a high oversampling rate. There is one more reason which I would like to explain to you. Again, this is more for you to understand how the reconstruction process is done, and so I would like you to follow along in that regard. Now the reconstruction process, what we call as the ideal reconstruction process. Reconstruction process says I want to take my discrete time samples and produce an Dirac delta train, which is excess of t with the appropriate scaling, and then I convolve with the reconstruction filter to get my reconstructed signal. Okay, so this has Dirac deltas, Dirac delta functions. Okay. Now, Dirac delta functions are difficult to work with. So, what we do is instead of Dirac delta, so we will say that instead of Dirac delta, we will use a filter or a function which is called the zero order hold, zero order hold. Okay. So, if I have a continuous time signal that looks like this, let us say that there is a, I need to draw it a little differently. Okay, so if I have Dirac deltas, they will have this sort of a scale factor. Okay, and this is what they have. A zeroth order hold is like a peak hold detector. So, whatever is the value, rather than thinking of it as a Dirac delta function, you think of it as a peak hold. It basically is a capacitor that holds the value of that, think of it as a voltage that is stored. When it comes to this next sample, it drops down and holds the new value, and then it comes here, it holds this value. Okay, so basically at every point, whatever is the height of the Dirac delta, it will hold that as the sample value until it reaches the next sample value. Okay, so this is called a zeroth order hold. Okay, so it's like a staircase approximation. So you can also refer to it as a staircase approximation. Now, a peak hold detector is something that we can easily design. It is a operation amplifier with a capacitor you can design. So this is a staircase approximation. Okay, now if you had a Dirac delta, we know how to do the reconstruction process. Now the question is, what is the new reconstruction if I use a zeroth order hold? Okay, so instead of a Dirac delta, this was the original, now the new one. So this is the old, this is a Dirac delta, okay, Dirac delta. The new is a zeroth order hold. This is the new. It has got a flat response between 0 and Ts. Until the next sample arrives, it will have a flat response. Okay? So, this is in the time domain, and the height of this pulse is equal to 1. Whatever is the height, you can scale it by whatever the height of the Dirac delta is. So, we call this as the zeroth order hold, H0 of t. Okay, so basically it is a peak hold detector. It has got this response. Now, the peak hold detector has got a Fourier transform that is given by H naught of j omega. This is equal to e power minus j omega Ts by 2. You can derive that, and this is given by 2 times sine omega Ts by 2 divided by omega. Okay, omega Ts by 2, and now here is the behavior of this. So, what is happening, this particular pulse shape is getting convolved with your Dirac delta. That's, you can think of it as this H naught of t is getting convolved with your Dirac delta to produce the staircase function. So, the new waveform, what is the spectrum of the staircase function? The spectrum of the staircase function, this spectrum, okay, will be given by the original xs of j omega. Because it is convolution in the time domain, it is multiplication in the frequency domain, H0 of j omega. Okay, so you take the original spectrum. What is that? What does that look like? Actually, very interesting. Okay, Hxs of j omega, what is it? It's basically all these copies of the spectrum. Xs. Okay, where is it located? Where is this one located? This is at 2 pi over Ts. This is 4 pi over Ts and so on. Those are the multiples. So, this is equal to omega s, this is equal to 2 times omega s and so on. You can look at these other center frequencies. Now, this h0 of j omega looks like this. h0 of j omega is a sinc function that basically comes up to here, then has got zeros. Basically, it has zeros at all the center frequencies. Okay, so this staircase function is actually doing a good thing for you. It is adding some additional suppression on these unwanted copies, because see, it is touching 0. Wherever you substitute the value 2 pi by Ts, it is going to suppress those frequencies even more. Okay, so it is doing a good thing in terms of suppressing. However, it does something that is undesirable. Notice that it introduces a spectral distortion in your desired signal. So, originally your reconstruction filter would have been like this, a flat reconstruction filter. Now, when you do the reconstruction, you find that what you get is not the original one, but it has been distorted by the 0th order hold. Okay. So, what we now do is we now have to modify the reconstruction filter to compensate for the 0th order hold. We don't take the original 0th order the reconstruction filter. We do a compensated reconstruction filter so that the distortion that is introduced by the 0th order hold is eliminated. Okay. Now, when you have the gap, notice that you have the ability to do this pre-distortion or distortion compensation that is introduced by the 0th order hold, because the 0th order hold in this case will go something like this. Okay, and it will go to the next point. So, the filter here has to have some compensation so that you take care of the droop that is introduced by the 0th order hold. So, this is the compensation for the 0th order hold, ZOH. Okay. So, why is it that we need this additional, this oversampling? For two reasons. One is you can build practical filters, and also in a practical reconstruction process, we cannot introduce Dirac deltas. So, those are more of a mathematical construct. So, what we can do is a peak hole detector, which is very easy to design. And so, you generate a staircase waveform, and then from the staircase waveform, you do a full reconstruction process through the convolution of the filter. Now, what is the filter that you must use? It cannot be the original filter, because there is a spectral distortion that has been introduced by the 0th order hold. We want to take care of that spectral distortion. We want to remove the unwanted copies, but also make sure that the desired signal, the spectrum, the copy that corresponds to m equal to 0 is not in any way distorted. Okay. I hope you are comfortable with that, and this is a important element. So, what the key points that we have talked about is the process of sampling, what sort of spectrum is produced when you sample a continuous time signal. Assuming that you have satisfied Nyquist criterion, we can always go back to the continuous time by using a reconstruction filter. Now, if you have exactly satisfied Nyquist criterion, you need an ideal reconstruction filter. If you have over satisfied the Nyquist criterion, we can design the reconstruction process with practical filters, and more importantly, we can also introduce the peak hole detector as a staircase approximation from which we generate the continuous time signal rather than working directly with the Dirac delta functions. Okay. So, what I would like to do is to leave with you one example which will be interesting for us to consider and also think about, and we will pick it up from here in the next class. So, let me give you the example. This is an example that is found in the textbook. ONS stands for Oppenheim and Schaefer. You can look at example 1 that is there in chapter 4. Chapter 4 is a chapter on sampling. This is example number 1. We are given a continuous time signal xc of t, which is given by cosine 4000 pi t. Okay. Now, this can be written as 1/2 of e power j 4000 pi t plus e power minus j 4000 pi t. Okay. And this also can be converted into a Fourier transform, xc of j omega, that will be given by pi, that is the scale factor. You have 2 pi as the scale factor for conversion from exponential to delta, but now you got a scale factor of half, so it becomes a factor of pi. Each of these exponentials will contribute a delta function, a Dirac delta. Okay, the first one is a Dirac delta which is centered around 4000 pi. The second one is a Dirac delta which is centered around minus 4000 pi. Okay, so the delta of omega plus 4000 pi is a delta which will be centered around minus 4000 pi.